introduce our speakers. So, first, Martin Beroiz is a postdoctoral researcher at the Center for Gravitational Wave Astronomy. He obtained his PhD in physics at UT San Antonio and UTRGV. His research focuses on the detection and automated discovery of transient optical counterparts to gravitational waves. Mario Díaz is the director of the Center for Gravitational Wave Astronomy, professor of physics at UTRGV, and director of the Cristina Torres Memorial Observatory. He obtained his PhD studying mathematical cosmology at the University of Cordoba and was a postdoctoral researcher at the University of Pittsburgh under the guidance of Ted Newman. Mario currently leads the efforts of the TOROS collaboration in the follow-up search for electromagnetic counterparts to gravitational waves. So first I'll give the mic to Mario. So everybody please.
I wanted to talk about the equation of state of neutron stars because I thought it was, it's a very relevant subject. But one of the things I discovered is I really want to learn myself much more about this. So I hope I can explain what is the motivation to get interested into the equation of state of neutron stars. And so most of my presentation is being stolen from this faculty member of Cal State Fullerton who gave a wonderful introduction to the topic at one of the LSC meetings for people that are just joining LSC and want to get tutorials. So they have a session of tutorial that run parallel to the business session. She ran over those tutorial sessions as I made this presentation. And I thought it was a very, very good introduction to the topic. And, actually the motivation is a very recent paper that appeared in, well, it hasn't appeared yet. From the format, you can see that they're planning to submit it to the monthly notice of the Royal Astronomical Society. But it was entered in the archives where pretty much physicists post all their preprints in, just 20 days ago. No, wait. Yeah, 20 days ago. Yeah. Today's November 1st, isn't it? Yeah. Last night was Halloween. Yeah. Okay. But I think it will be published very soon. And the title of the paper is A Long-Lived Neutron Star Merger Remnant in GW 170817, Constraints and Clues from X-ray Observations. So this is the same team that actually performed X-ray observations right immediately after the kilonova explosion on August last year. But they've been doing observations at a later time. And this is what, one thing I did is just pick up their abstract and broke it down in bullets. And essentially, this is what the abstract says. Multi-messenger observations of gravitational wave 1708-17 have not conclusively established whether the merger remnant is a black hole or a neutron star. Well, to start with, it's not even completely clear that the two objects that collided, the two compact objects that collided last year in August 17, were both neutron stars. One of them could have, in principle, been a black hole. We know that they weren't both black holes because otherwise we would have never seen gamma reversed, electromagnetic radiation seen in the optical and so on and so forth. But because the information is not coming as clear cut as it could be coming, we don't know, we cannot with certainty rule out that the other object is not a black hole. Most likely because of the mass, you can say it should have been a neutron star because they're low in mass. Neutron stars are supposed to have masses between 1.4 solar masses and not much more than 2 solar masses. But that upper limit is not clear. And to some extent, I'm going to explain why it's not clear. And so this observation showed that a long-lived magnetized neutron star with colloidal field B equal 10 to the 12 Gauss is fully consistent with the electromagnetic data set when its spin-down losses are dominated by gravitational wave emission. In other words, they claim that recent observations could sustain the idea that even the merged object wasn't a black hole. It's still a neutron star. And the reason for that is electromagnetic detections that are still making from the object. Now, in order to have, what is a colloidal field? Who knows what the word colloidal means? Does anyone here know what the word colloidal means? Well, I didn't know either. Yeah, I'm not going to explain how to remember. So just search for it. And essentially, most of the electromagnetic fields that are associated with the stars, and particularly with collapsed stars like neutron stars, most stars have magnetic fields. That's the reason why you have sunspots in the sun. When the objects collapse, they start spinning much faster. They're a source of electrons that are lost and create electrical currents, which means the magnetic fields intensify enormously. So they get very strong magnetic field. And typically they have what is called a toroidal shape. And a torus is essentially donut. So this is the shape. So the toroidal component of the magnetic field is going to be in this direction, in the blue arrow. And the poloidal comes from poles. So it has this particular direction. So it's orthogonal to the toroidal component of the magnetic field. In other words, it seems that if you really detect poloidal fields, this could be consistent with the fact that there are spin-down losses that were mainly triggered by the gravitational wave emission. So in gravitational wave, it's losing energy, it's losing angular momentum, and the star slows down. Now, in order to have this type of field, the star has to be, it cannot be a perfect sphere. And it has to have an ellipticity that has to be larger than this. Notice that this is very minimal. 10 to the minus 5 is actually a ratio between the semi-major axis in one direction and the semi-minor axis in the flattened direction, and or vice versa. So this ellipticity can result from a toroidal magnetic field component much stronger than the poloidal component, and the configuration is expected from a neutron star newly formed from a merger. So abrupt magnetic dissipation of the toroidal component can lead to the appearance of X-ray flares. So the sort of losing of energy in the magnetic field can generate X-ray flares. So X-ray explosions like the flares you see from the sun, analogous to the one observed in GRV afterglows. I'm not an expert in this field, so I'm talking a lot, but I really don't know much. So probably one of the reasons why you have this X-ray flares, because this magnetic field that is intensifying or is being lost is channeling also electrically charged particles from the surrounding medium and the remaining accretion disk, and that's creating this flare. So that I personally I'm interested in learning more about the astrophysics of these objects. So in the X-ray afterglow, the authors claim, that's the reason we say we identify a low significance temporal feature 155 days. So this is roughly a little bit less than 6 months after the event was August last year. So these are measurements that made barely a few months ago, consistent with the sudden reactivation of the central neutron star. So the energy injection from the neutron star spin down into the relativistic shock is negligible, and the line continuum is fully accounted for by a structured jet seen off-axis. So it's not aligned with the axis of rotation. Where radio and optical observations probe the interaction of this jet with the surrounding medium, observations of X-ray wavelengths performed with liquid sampling open a privileged window onto the merger remnant. So they're claiming that it's important to observe this in X-rays now, to keep observing them. So notice that this is pointing at the possibility that there is a neutron star there and not a black hole. I don't think they can claim that they know that that's the case. They're just speculating that could be the case. So that's what's interesting about the paper. So further studies are required. And but all this is a motivation to take a look into well, what is a star? So I know that many of you in this audience are undergrads, so we haven't had many, or maybe not even one at all, class in astrophysics or maybe even quantum mechanics. So I'm gonna do I'm gonna run a few slides with as little mass as I can, because I don't think it's all that important to understand this. Eventually, if we want to understand more, the math is important. So, a star to a great extent is a compromise between the thermonuclear forces that are exploding at the core of the star, where tremendous energies and temperatures are fusing hydrogen with hydrogen and making helium. And so that's the thermonuclear process. And gravity itself, that all it wants is all the matter to get together. Gravity is extremely loving. It wants everything to get together and packed. And so eventually, when the hydrogen that is being converted to helium is exhausted, the star is going to start fusing helium into heavier elements, but eventually it's going to run out of elements that can be fused. So typically, a star can only make elements as heavy as iron, carbon, oxygen, and not much heavier than that. It cannot make things like platinum, gold, polonium, and a whole bunch of elements that can be manufactured, but you don't find in this type of stars. Although they're found in the universe, we find it on Earth. And that's the other part of the story that is interesting as well. And so, what happened when they ran out of fuel? If the star is not much heavier than up to 1.3 times the mass of the sun, I think the exact number is 1.44, which is called the Chandra-Sekhar limit. By making certain calculations, we show that the stars that can collapse into something called a white dwarf, and a white dwarf essentially is made in this manner. So, hydrogen atom is essentially proton, because the nucleus in the hydrogen atom only has a proton in the center, and it doesn't have a neutron, and it has an electron. Now, to get an idea of how much vacuum is in the hydrogen atom, you think that if the proton had a 1 meter radius, actually the proton is 10 to the minus 19 in meters. So it's not even with the microscope you can see that. But let's say that you make it big, up to 1 meter radius, a proton. Then an electron, it would be 300 kilometers apart. So this is how big the space is between the proton and the electron. So now, when the star runs out of hydrogen and helium, and gravity wins and is collapsing, there is a tremendous pressure that essentially is going to break down atoms and the atom structure, and what you're going to get is objects that are going to be collapsed, and that huge volume that in principle was there doesn't exist, it's not available any longer. And but there is a limit in how much it can collapse. It's given by something called the Pauli exclusion principle that says that not two atoms can be in the same quantum level of energy. And which means they're piling up with this quantum restriction, but at the same time, now that the volume is so small, because there is that restriction, one thing that happens is now they're not going to be the electrons, they're not going to be spread out over a large volume, they're going to be concentrated in a much smaller volume. Heisenberg principle says that now if they have a small uncertainty in the position, and the reason why it's going to be a small uncertainty, because now they're much more localized because of the collapse, and then it's going to be a large uncertainty in the momentum. That means they're going to try to increase the velocity, and means they're going to increase their pressure. And that pressure that is being increased is what sustains the star. So that dead star is a white dwarf. And typically white dwarfs are around a solar mass about the size of the Earth and radius 6,000 kilometers. So that's typically what, run out of battery. Well, I hope we can still. And now, what happens when they're more massive than 1.4 times the mass of the sun? So they have gravity, they have enough gravity now to keep pulling in. And essentially what happens is that electrons and protons annihilate themselves, generates neutrons and neutrinos, but all is left, they're neutrons. So the star is just a soup of neutrons. It can collapse further, and what you get is a neutron star. So a neutron star is a star more massive than the 1.4 times the mass of the sun, and it's all the neutrons packed together, the protons and the electrons have disappeared. Neutron star, typically, I don't think I have it here, yeah. Typically what happens with a neutron star is that it's going to have a diameter of, and here comes the big if, between 10 to 12 kilometers, but it's highly uncertain, we don't know. But we know it's of the order of objects that are much larger than about 10 kilometers in radius. And why do we don't know exactly how big it is? Because what is the state of matter at that high energy densities is something that we really, really don't know. So let me go in a crash course on high energy physics now, which is, yeah, the laser doesn't work. Does someone have a laser pointer? Probably not. No, well,
There's a stick there. If you need it.
so, oh yeah, great, thank you. Yeah, that was it. So how is nuclear matter built? Well, you know that electrons are elementary particles. You cannot divide it or break it apart any further. That's what they are. But protons and neutrons are actually made of a smaller elementary particles that are called quarks. Quarks come in many different flavors. They're like a zoo. I even myself cannot say, you know, I know how many they are, but I really don't know much nuclear physics myself. And that I never got very interested in nuclear physics. I only started to get interested in nuclear physics now because of these guys, and I try to explain a little bit why. So protons and neutrons are composed of these things called quarks. Quarks are described by something called quantum chromodynamics, which is essentially the strong nuclear forces. You know, there are four basic forces in nature: gravity, electromagnetism, and the nuclear force. The nuclear forces could be weak, responsible for the reactive decay, or could be strong. Strong are the ones that made up protons and quarks. Now, so in general, all the particles made out of from quarks are called hadrons, and nucleons are the protons and neutrons. But then you can also have made out of quarks. These mesons that are pions counts, they're made up of 2 quarks. And then there is this thing that it's not known very well, it's speculated, called hyperons. Hyperons are essentially exotic baryons that include some strange quarks. And then a super-4 matter that is not very different, but it's, they're not even neutrons. They're something more fundamental or basic than neutrons. So all this is the realm of high-energy physics. I'm not a high-energy physicist, so I really know very little about it. I know just a few of the names, I know much more than that. But if you go and look at the chemical, the periodic table of elements, you can construct this table, and you see that depending on the electron distribution on their shells, you can divide it in different type of classification: metal, non-metal, basic metal, halogen. Actually, for astronomers, it's interesting because astronomers, anything that goes beyond lithium and beryllium, they call it metals. Yeah. And now, look at this other picture. So if you look at this one, let me go back because there's something that should say here. So this is hydrogen. Hydrogen is made out of 1 proton and 1 electron. So this is the simplest element you can make out of the elementary building blocks of matter. But you can keep adding the things to get helium now. You're going to have 2 protons, you're going to need to put neutrons, and you're going to put electrons there to balance electric charge. Obviously it's heavier, but you keep doing this. It's like a game in which you keep adding protons and neutrons and electrons to balance electric charge. And that's the way all the chemical elements are made. Well, how far can you go? Can you have 1,000 protons and 1,000 neutrons in a nucleus? And, well, the answer is, as you probably imagine, no. There's sort of a limit. In nature, actually, you only encounter up to some extent. I should have put it here, but there's a chemical table of elements now that are shown how they were formed. We know that this was formed at, slightly a few 100,000 years after the beginning of the universe. And then helium, so they were made during what is called the nucleosynthesis after the Big Bang, the big explosion. But then, the other ones are formed inside stars. But then, when you go beyond, particularly silver, cadmium, palladium, all these heavier elements, they are not made in stars. We know some of them are made in core collapse supernovae, which are stars that collapse and form neutron stars, but most likely a lot of them are made in the collision of neutron stars. So if you make a diagram of protons where this axis means you keep adding protons, and neutrons where you keep adding neutrons, you cannot put it arbitrary number of protons and arbitrary number of neutrons. It turns out that there is a balance to get stability in nature. If you get too many protons, you get radioactive decay. The same if you put too many neutrons. And actually, this line here is called the neutron drip line. This other one here is called the proton drip line. So you cannot find elements that are stable between these 2 lines. And typically, like the Greeks would say in life, you find things sort of in the middle. And after a certain point, they're not stable, they decay radioactively. And now you can make another diagram in which you put pressure and you put density. And the reason why you would do that is because precisely equation state, when we talk about equation state, is relationship between thermodynamic variables: pressure, temperature, volume, energy. So pressure between energy or density energy. Then we have in this area electrons that are non-relativistic, but here, which is essentially the line that is along the neutron drip that I mentioned before, you're going to have things where there is a degeneracy in the neutrons that are being packed together and make pressure. So here's the pressure that the electrons made that give you the limit of white dwarf. Here's where you start the limit of neutron stars. And this is essentially what we are when we're looking at neutron stars. I'm going to skip other aspects of this because it's going to take too much. Now, regarding nuclear state of matter, so if you look at the neutron star, most likely what you're going to have going from the crust to the core of the neutron star, most likely the neutrons and matter is going to be in a very, very sort of deformed shape inside the neutron star because of the tremendous pressure they are. So much so that this is a state that is called a pasta phase because the neutrons are like a spaghetti here. And so solid crust is the body is sort of centered in a cubic way, like in crystals, but then the mantle is going to be like nuclear pasta, and then the outer core, they're going to be neutrons and protons sort of loose with maybe a few electrons. And so what happens about nuclear density? Well, we really don't know that very well. And let me tell you why. I'm going to skip probably a few slides. So about nuclear density, it seems to be a single function that you get for something called the standard model of particles. So the standard model of particles is a quantum theory that was developed in the 60s and 70s, joining electromagnetism with the nuclear forces. And this is what you need to apply to neutron stars to understand what is their structure. In the low energy limit, the nuclear physics of nuclear interactions, you're going to have symmetry energy that goes from the nuclear to the neutrons, and something that are what I call effective field theories of particles and interactions. Honestly, I know very little about this myself. But these are very highest densities, and at very highest density you might be encountering something that is called asymptotic freedom. So what happens is the following. Strong nuclear forces are extremely short range, which is weird because they're strong. The strongest forces that you have in nature, they only act over extremely, extremely small scales that are even subatomic. This is the realm of what high energy physics study with accelerators and bombarding particles and all that. What is interesting is they cannot get to study things in their accelerators that are like these neutron stars. That's the reason why a lot of the nuclear physicists now, they got so interested in astronomy because of what neutron stars can show. And I think I'm going to be going beyond my time. So let me tell you just one more thing. What happens about the nuclear density? Well, there is an intermediate regime that you need to compute it using, it's very powerful supercomputers. And actually, the works that you do are constructing what is called quantum chromodynamics in the lattice. I know how to say this name, which means I sound like I know what I'm talking about. I don't know what I'm talking about. This is what people would do with supercomputers that work in quantum chromodynamics. And it's a lot of work. I mean, it's really hard to get you to make predictions because it takes a lot of computational power. But of course, this is because of the powers of supercomputers now, there's a lot of work being done. So, but it could be, additional particles in many states that they're not really calculated. So we don't know very well what is the regime of the strong force that is needed to make these calculations and to have accurate predictions. In other words, there are few experimental constraints for high density and neutron-rich matter. That's one of the reasons why it's so interesting to understand what happened with neutron stars. And Well, it doesn't show in a diagram, I don't think is. I think I'm going to stop here. So, in other words, neutron stars, just by observing them with gravitational waves, with electromagnetism, the optical, getting light curves, can, over a period of time, let us have a better estimator of the energetic processes that are occurring inside neutron stars when they collide. And that could lead to better understanding of these theories of quantum thermodynamics and strong nuclear forces, and maybe even up to some extent how they get tied to gravity as such strong regimes. So, in other words, my point, this is an extremely exciting area. I would be very interested in the students wanting to read more, a lot about this. You know, they throw a lot of words, and I myself need to read about them. But I never thought that nuclear physics was going to be so cool. Anyway, I want to stop here because Martin needs to keep going.
Hello, everybody. I would just like to talk about a paper that is not yet published, but it's from David Radis et al. Binary neutron star mergers, mass ejection, electromagnetic counterparts, and nuclear synthesis. They basically did.
This, the laser pointer is not working, but you can pass. I mean, it would.
So they did not submit it, but they basically did 59 neutron star merger simulations and extracted a lot of information about it. So my talk is gonna first start with some intro to the topic, then I wanna review some of the physics equations that they use, especially general relativity, particle reactions, and the neutron star equation of state, and some of the astronomy predictions that they do, especially the ones that are particularly interesting for us, the optical ones and radio, light curves, and some particle production rates. And then I'll go to the conclusion. So neutron star mergers, these are the source for gravitational waves, electromagnetic radiation all across the spectrum, and neutrinos. So these are truly a multi-messenger source for astronomy. As far as I know, I think this is the most messengers of all of them, but there might be. I like this phrase in particular because it's not just multi-messenger, but it's also multi-physics. This phrase is from the paper. It says binary neutron star mergers are essentially multi-physics problems involving strong field gravity, strongly interacting matter, relativistic magnetohydrodynamics, and neutrino transport. So you get all these physics put inside, and that's another remarkable thing, that this is one of the phenomena that relates the microphysics, the microcosmos, with the macrocosmos through orders of magnitudes between the source and the cause and the effect. It's one of the most impressive stretches of physics, I would say, and that's why also it's so difficult to simulate. So why do we need numerical simulations? Like I said, it's a multi-physics problem, but we need accurate predictions of the quantity and composition of material ejected to fully understand the origin of the heavy elements, heavier than iron and stuff. And then observations are also important because they will constrain the parameters of these simulations, and then with the constrained simulations, now we have more accurate predictions on production rates, for example. So numerical simulations are extremely useful, but they need to be up to this point. People either treated GR as an approximation or the particle physics as an approximation. This is the first time they do a pretty complete full simulation with all the dynamics. So as I said, this paper presents the largest set, 59 neutron star simulations, with realistic microphysics. They went to atomic and subatomic particle reaction, nucleosynthesis, the composition and energy. The dynamics of the whole system is simulated in general relativity with magnetohydrodynamics. They consider the neutrino production, losses, and also they consider reabsorption in 13 cases. This is going to be important actually for the light curves. They consider viscosity in 6 cases, and they saw some interesting results regarding viscosity. Even though they didn't go too deep, they said that they're going to release another companion paper. They was probably going to that details. And they tested 4 different equation of states for the neutron star. They consider total binary masses. This is the combined masses between 2.4 and 3.4, and the ratios between the biggest and the smallest between 0.85 and 1. They're pretty complete numerical simulation. 59 may not seem like too much, but they studied quite a few cases. I'm going to go into what are the elements, or what are the physics equations for people that I put these equations only for people doing GR now, because it might sound familiar to some of you. But basically they used, this is conservation of the number of either protons or neutrons. They consider a classic, your normal perfect fluid. And this is the usual conservation of the energy momentum tensor. You will notice that the first and third are usually equated to 0 when you have conserved quantities, but this is not a closed system in the sense that you have sources, external sources that come from the particle creation. This R source term is the net lepton number, the position rate due to absorption and emission of neutrinos and antineutrinos. This is basically how your number of protons and neutrons change, because it's not conserved, because you are creating actually these elements. And this Q is the source for the position rate due to absorption and emission of neutrinos. It's basically the same thing, but for energy. One is for number of leptons, and the other one is for the energy. And with this one, they build the initial data with package specially designed for that, and the full GR will provide them with all the tidal interactions between the 2 neutron stars and the shocks and the dynamics.
They propose some relationship of P and E, equation of state.
Yes, and that will probably come from. I have to say I don't know anything about the equation of state of neutron stars. I just know that I have a slide for that one, but I wouldn't know much how they relate these two. Yeah, I would guess from the equation of state. This is, by the way, just the usual densities, just they call it E for some reason. And on the particle side of the equation of the ingredients, they consider all these 7 reactions. Each one has a companion paper that tells them how to compute neutrino production. These rates R and Q that I showed before. So they do it with these formulas described in the paper, then they feed it up back into the GR, move the simulation forward, and this R and Q actually gives the kappa terms, which are basically related to the transparency or opacity of the medium, and the opacity in terms gives how transparent it is, gives you how the light curves will look like. So it's all tangled. These are like I said, I don't know anything about neutron star equation of state. I'll just list them here: DD2, VHP, LS220, SFHO. This is based on a liquid droplets Karami model, whatever that is. And these are the numbers that are the maximum mass for a non-rotating cold neutron star, and the maximum radius that the equation of state predicts. So to have an idea, the heaviest neutron star known is 2.16 solar masses, and so this might be pushing the limit a little bit. All of the others are in the ballpark, but I have to remind you this is for non-rotating one. So if you have a rotating neutron star, you can have more mass. It's contained by the rotation. And the radius in kilometers, they're all order 10, as it's supposed to be. They're all reasonable physics, reasonable, consistent with observations. So with all these ingredients, what did they get? 10 to the minus 3 solar masses of material is ejected dynamically during the mergers, and the ejecta is actually pretty important to know how much and what composition it is, because these depend heavily on the binary parameters and the neutron star equation of state. So it's important to know how much and what's the composition. About a millionth of a solar mass is accelerated by shocks to speeds up to greater than 0.6 C. They mentioned in the paper that this might be a controversial point in the sense that some other teams got this similar result, but it's hard to tell if it's a numerical error or if it's actually significant, since it's like a small one. They say that it's actually significant, and this produces bright radio flares. Even weeks, months, or years after merger, this is quite remarkable. And the observation of these radio flares could constrain the equation of state. So, because it has to do with the neutron star balance after the merger. This is another main result. This is the production of the different elements. This is the atomic number, and this is how relative abundance of each element there is. One thing to notice is that there's like 3 peaks in all of them, 3 peaks of production, and the second and third is pretty robust in all of them. Like no matter what the simulation, this second and third peak is like always there. The first one changes a lot, and it changes the most with how they treat the neutrinos. So this first peak is very sensitive to the neutrino treatment, whether they consider the losses and their reabsorption and how they do it. These are different models. Not so sensitive, but also a little bit sensitive. It's the first peak is on the binary mass ratio of the system.
What are the colors?
The colors are different models that they use, different simulations, individual simulations. This is the simulation with this equation of states, with these masses, and this Lx, LTE, and M0 are the different ways they treat the neutrinos. And in this one, they keep the neutrino fixed. The equation of state
and the
fixed.
horizontal axis is?
This is the atomic number.
Atomic number, right?
Yeah. So it doesn't, like, depending on, for example, this is 1.35 and 1.35 equal mass. It's in blue. 1.4, 1.2 is the other one. So if they're not equal, it will give you a different production, different relative quantity of different elements.
And the green lines are the same in all 3 graphs, right?
Yeah, the green line is just for reference into solar production. Yeah, abundance. Yeah, the green is just reference.
What is the atomic weight, the atomic number for iron? Huh? 58. So essentially, it's everything heavier than iron that is being plotted here. So it's showing the relative abundance of heavy elements.
For example, the equation of state doesn't seem to play a role, like pretty much at all in the. So it's pretty insensitive to the equation of state, which kind of makes sense because this is most for unbound particles. Another prediction they make.
Can you go back?
Yeah, sure.
Back? Because one thing I remember when I first, got interested into this, there were some people that knew a lot. There was a guy, what was his name, working in Los Alamos. Right? He's still working in Los Alamos. He essentially calculates production of elements in nuclear reactions. And one of the points was they were expecting to be so many really heavy elements, lanthanides, created in kilonovae, that there were so many free electrons that were going to essentially take a lot of the energy, and that's called electron opacity, and things would have been hard to observe in the visible region of the electromagnetic spectrum. To the contrary of these speculations, the kilonova, which is the only one that we've seen so far in the history of humankind, happened to be pretty bright and blue, and and it evolved pretty quickly to the red. And now I see that the second and third model, and I would like to know the difference, are the ones that predict a larger abundance of relatively lighter elements respect to the heavier ones.
You're talking about this thing?
That one and that one. But that one not all that much.
This one, yeah. And actually, yeah, this one is pretty low. This is varying the neutrino treatment. But their conclusion is that neutrinos play a crucial role in the production of the elements.
Yeah, there's such a high flux of neutrinos, it probably changes the density, and that changes the reaction rate.
Yeah, I will need to read this and understand it. I don't understand it well, but at least I see what they claim.
Yeah, the paper is packed with information,
I can't tell.
and I try to do as summary as short as possible. But there are a lot of even more graphs and more data. It's a pretty good paper. I like it. These are the kilonova light curves. There you have 3 different scenarios. This is prompt black hole formation. That means they merge and immediately goes to a black hole. This is called the hypermassive neutron star, intermediate. This is a case where they merge, they form a large neutron star that is somehow unstable, only supported by rotation, but then that rotation quickly slows down and collapses into a black hole. The time is like the decay time is 7.7 milliseconds. So it's very intermediate neutron star, and this is a supramassive neutron star in which the neutron star manages to stay much longer. It says greater than 30 milliseconds, but it actually can go up to seconds. So this can be, and the general trend is that the longest the neutron star survives, the stronger the signal and the bluer the signal. And it lasts for the longest. This is 3 different bands, G, Z, and K. This is radio, 2 opticals, 1 radio. That's basically it. Then they make some remarks regarding observability during the next science run. They say using a detection of horizon for advanced light of 120, 170 megaparsec, they estimate that kilonova counterparts will be detectable for a large fraction of the neutron-star merger. If you have a neutron star that lives long, then the kilonova will be detectable in the G and Z bands, and in radio, obviously, much even further. So if the black hole is if the black hole forms very rapidly, so that there is no hypermassive neutron star, it says it would only be detectable in the radio band, this K band, up to 30-50 megaparsec, depending on the orientation, kilonova, they will be detectable in the CG band. This is just, it basically says that they are, it's very promising. So overall, the idea is that we're gonna probably have many, even though we don't actually know the neutron star rate in how many of them you normally expect. They are confident that we will get most of them, if not all of them, or a huge fraction of them. So for conclusions, the paper, the Beroiz et al., they run 59 numerical simulations, neutron-star mergers. They consider 35 distinct binaries with masses between 2.4 and, this is combined masses 2.4 and 3.4, mass ratios between 0.85 to 1. They use detailed microphysics in a fully GR setting, and they consider 4 different equations of states. They generated kilonova light curves, and they confirmed that they depend, it was already known, but they confirmed that they depend on the lifetime of the merger remnant. They found, by the way, according to what they discovered, it would suggest that GW 1708-17 would have had either a hypermassive neutron star or a supramassive neutron star. That doesn't mean that it may be that right after the merger it became a black hole, but probably had an intermediate neutron star. And another important thing is that they found a clear correlation between this color, between optical and radio, and parameters of the equation of state. So it seems like a joint observation between radio and optical could constrain some of the parameters in the equation of state with this sort of observation in different bands. And that's it.
You helped me a lot with the proposal I need to write. You know, we submitted a proposal to the camera for TOROS. And this, I want that's the conclusion slide.
Oh,
I'm going to be using it.
I'm happy to help.
Yeah.
So under none of these simulations that they made, there's no scenario where there is a resulting supermassive neutron star that remains longer than you said, maybe second, right?
No, because I think that the total simulation is, didn't go any, I think it's seconds after the merger.
So no simulation where it lasted longer, so that maybe it could trend or related to your talk where they say that if possibly there's still a neutron star there after the kilonova event, right?
Yeah, you know,
Yeah.
I think that there might be some.
And according to this model, it seems that it's very likely that you still can get neutron stars out of these simulations, which would be, like he said, consistent with what the guy from it's not the Fermi group, it's the European X-ray. I would say the European Space Agency X-ray satellite called. Anyway, it's most of the people from the French, Italian team, Piro, and then that have done this analysis of the. I don't know the NASA people with Chandra have done any analysis lately of this.
But there, so I think there is, but I don't know. They did so many.
Okay.
I don't remember. But I think I saw one of the graph for one that is stable neutron star after.
Okay.
But I'm not sure.
A lot of those models will have a hypermassive object that, after the merger, exists for only a few milliseconds, but then might collapse again to a black hole.
Right.
Because it's very unstable. But that's like a majority of the models. But there are models, like you said, that are stable for a long time.
But if they take the X-ray emission, months after the event, that means that. Well, I'm not sure it means that you could still have a black hole. I don't know.
Probably could.
Well, with an accretion disk.
Yeah.
It won't live long, like, how are they called, the X-ray binaries, where you have a star that is feeding the black hole and creating the accretion disk, like signal 6-1. But you still, you see could get an accretion disk and the thing is gonna, live for a while. I don't think for too long, but.
Depends on how much mass was initially released from the merger. If it held on to a lot of its cocoon and a black hole formed, then it might have enough matter to power for a while. But if it lost a lot of that cocoon, then
Yeah, but it is what it is, which means you won't get anything more from any other object in the vicinity, which means eventually it's going to die off.
You mentioned before the results about calculating opacities. So is it essentially that if you're computing light curves from equations of state, you're really using the nuclear physics to calculate opacities, like relative opacities, and then that is how
I think
you
it's
produce light curves?
yeah. I think it's tied. I don't know exactly how they do it. I don't know. I don't even know how they do it. But opacity is related, as far as I understood, to two things: to the particles that you're creating, and the equation of state for the neutron star. How those two things interact, I don't know. I don't really know.
Any other questions?
Maybe you mentioned about the rate that it's ejected from the binary. How is there any indication how it might vary depending on the masses? Because if the masses are not equal, because
Yes, sure. There are a lot of graphs that I didn't present, but if you go back to the paper, it's probably in there because they do. The ejecta has its own. I didn't touch like treating the ejecta, but they do talk about that in the paper, but I didn't put it here.
would it be significant in terms of the counterpart, the number of mass that is ejected? Well, is it very pretty much, or just smooth if the ratio is not 1 to 3 like black hole neutron star?
Yeah, that's interesting. I don't think they. I'm trying to remember if they have any, because they do these comparisons of how the models change by changing the parameters. I don't know if they have in the amount of ejecta. I don't remember.
Anybody that is interested in this, I can
Yeah.
suggest further reading, and then eventually we can try to pursue it. I'm interested in this. That's cool.
Yeah, that's cool.
Yeah, and we're going to be observing kilonova. We really try to understand the physics behind, not just,
Not just observe.
yeah. So,
Is there a way to access it before it's published?
Yes, it's actually, I think it's the archive, and I can provide a link if you want.
I'll link-
You guys came a couple of weeks ago for the seminar Women in Science, right? I hope today you were coming thinking that today was the seminar for women in science. I'm sorry, it was last week, but it's on YouTube. Can you, Richard, can you provide them the link?
Yeah, I mean, before, because I could just show it on here, but any other questions for Martin before we adjourn? Okay, well, let's thank our speaker.